Okay, so today we'll start a new topic, which is the radiation effects on memory devices. So we will split this lecture into two. So today's class, we will focus on one particular mechanism called total ionizing dose effects. In the next class, we'll talk about single event effects on mostly the mainstream memory. So like SRAM, DRAM, and flash. So these are my topics that I plan to cover today. We'll talk about the motivation and the background for this study, and we'll talk also about different fundamental mechanisms that radiation can cause. Then we'll go a little bit particular about the flash, how radiation effects cause data corruption in flash memory, and then finally we'll talk about TID, or TID short form is total ionizing dose effects on DRAM as well as SRAM. Okay, so that's the plan, and yeah, with that, let's go ahead. Okay, so space is increasingly getting crowded with different satellites, specifically microsatellites, right? We're talking about very small scale satellites, typically built with commercial off-the-shelf electronics, because those satellites are designed to last not for 10 years, maybe 10 months, or maybe a couple of years, right? So there is no point of designing them with very high cost, red hard process, right? So they are mostly the commercial off-the-shelf electronics are used in those satellites. And with this increasing number, I mean, studying the radiation effects on commercial off-the-shelf electronics like your solid-state drive, right? Flash-based solid-state drive, DRAM, SRAM becomes very, very important as well. And this chart we show, one is this the satellite constellation, right? So in this plot, right, if you look at those dots, these are basically individual satellites. Now, problem with this setup is when you have increasingly number of satellites, the communication with the base station becomes a problem, because base stations are few on the Earth. You cannot communicate with the base station at any time of the day. You have to be on the line of sight. You have to be exactly on top of each other. And then the link, right, this radio frequency bandwidth that through which you can communicate between satellite and base station is also very small. So that means you cannot, right? One is few number of base stations. Second is if you have so many satellites, then having line of sight window is very restricted. You have very slow communication link, right? RF bandwidth link. So that's why the proposal is, or this thinking process is, we will have few data center in the space itself, so that you don't need to always communicate with the base station for data processing. You can do processing in the space itself. So there's a lot of interest. There are several startup companies, government agencies looking at setting up data center or data center for satellites at this space. Right? Okay, so that's the motivation, that why we need to study radiation effects on those electronics and all. And data center will have FPGAs, will have memory, processors, everything together, and everywhere failure can come in, right? So you have to ensure all those components of the data centers are red hot. Okay, so that's the motivation for studying radiation effects on space-based system. Now, there are issues, right? These are the radiation-related failures are real. For example, if you look at the news articles, right, there are ISS stands for International Space Station. So they had a supercomputer built of commercial off-the-shelf electronics. I think HPE. That HPE was the one of the builder for this this supercomputer, and what they found that 50% SSDs, and more than 50% SSDs, actually 11 out of 21 SSDs failed in that supercomputer. Since they built some redundancy, they could still recover the stuff, but I think that's NAND failure is one of the main cause for, or is one of the main failure mechanism in the space system, right? ISS is International Space Station. Not only that, there are many other incidents. You can see Voyager 2 has bit flips mostly coming from this data corruption issues in memory. So bit flips in memory caused by radiation is pretty common in space electronics. So this is another incident, 2010, the zombie satellite, because this Galaxy 15, which is geostationary satellites for Earth, it also got affected by radiation, space radiation. It causes single event upset, right? Those single event upset means suppose a SRAM bit got flipped, right? Or some configuration memory file got corrupted. Then the entire system will be failing. So this satellite lost command control but kept transmitting, right? That's how this zombie satellite name came in. And then SpaceX recently, there are issues with SpaceX as well, that just after launch, more around 40 satellites got lost due to this geomagnetic storm, again radiation related issues. So yeah, so those are real problems. So if you look at, this is just few I just quoted just to sensitize, the radiation induced failures are real. And if you want to do something with space electronics, you have to take care of radiation effects, okay? Any questions, any thoughts so far? Okay, so radiation issue is not just for space, even for terrestrial system, like say data centers and all, you see this issue. Less because we have ozone layer which shields some of the high energy radiation, right, which less particles can come in, but still there are still some high energy particle penetrate through this ozone layer and comes to this Earth atmosphere, right, and can cause similar upset in the memory bits. So to give you a few examples, this is one famous example on Belgium voting. The voting error in Belgium, it happened that, okay, there's one bit got flipped, right? So depending on which position in an integer representation, right? So this is 2 power, how much? 2 power 12. At 12th bit position, it got flipped. So 2 power 12 is 4096. So that's the extra vote, and that caused some. So this incident has been thoroughly studied, and if you are interested more, this is the link, you can take a look. But this is one example of terrestrial, right, radiation effects at the terrestrial. This is another example where this Qantas flight, suddenly their electronic system, right, got corrupted, and they felt like there is some attack happening, but it's not. This altitude information got corrupted suddenly, and then the flight has to do emergency landing, and because it's happened so suddenly, there is a lot of issues in terms of casualties and all. Not only that, it's very interesting effect is on this DRAM, right? So it's coming from packaging material. Interestingly, this was first captured or first reported in 1970s by Intel's DRAM. What they found, so they have a plant that time at Green River in Colorado actually. And what happened, there is some contamination. This river was passing through a mine, which is uranium. So through that, some uranium radioactive material got contaminated in the packaging, IC packaging, that's like ceramics. And very tiny amount of radiative material can emit high energy radiation intermittently, and that can cause single event upset inside the DRAM. So that is a known issue. And whatever I'm saying is well proven. It's not like hypothesis. People have done thorough research, and those links will help you if you want to know a little bit more about those incidents. So you can see that radiation effects is not just an issue for terrestrial, not just issue for space-based system. Even at Earth, even at terrestrial, it can cause data corruption. And currently, if you go to many conferences, the silent data corruption is a big, huge topic, right? So silent data corruption is in a big data center. There are multiple issues because data center has huge amount of electronics, right? Zettabytes of bits. So your scale is high, so variability itself will be high. But one of the main reason for this silent data corruption in SSDs and other system is through soft error. Soft error means an error which is not permanent. It is whenever radiation or high energy particle goes through your electronic system, it causes upset, right? This is not a permanent failure. It causes an upset. If you cannot detect it, it remains silently in the system. So the silent data corruption in data center, if you just type in Google, you will find a lot of material, a lot of issues, a lot of funding as well to identify the root causes, right? So one of the root causes is also radiation effects. So I hope I have convinced you that it is not just space electronics. Even for Earth-based system, radiation effects on memory devices specifically is a interesting topic or is an important topic. Now, if you look at what are the particles we should be worried about, or what are the particles which causes these radiation effects, there are heavy ion, proton, neutron, electrons. These are all coming from Van Allen belt, right? Radiation belt across the Earth. So those are radiation-prone zone. So if your satellite comes to those zone, which is then you can see a lot of radiation, storm radiation here, upsetting that. So that is one of the sources. And can characterize them as particle. Particle means it has some mass. But there's another type of radiation which is photon. It can be X-rays, gamma rays, right? For imaging technique. For example, you go for dentist, they took image of your tooth, right? Through X-ray. This is also ionizing radiation, which is photon. Photon means no mass. So, but still they can cause damage in the device structure, right? And based on energy, you can see their penetration depth. So if even high energy gamma rays, for example, it goes through not only skin, wood, cement, everywhere, right? So that's the strength of those ionizing particles. Now, in terms of electronics, so these are the three main important effects that we'll be talking about, or it causes in terms of electronics. One is called total ionizing dose effects, right? So typically the insulating material, right? What is the most common insulating material in silicon technology?
Silicon dioxide.
Silicon dioxide, yes. Silicon dioxide is the most common insulating material. For example, in flash, it is used as a gate stack for SRAM, DRAM. It is used in the access transistors, gate oxide. So that part gets affected by total ionizing dose effects. So what it will do that after total ionizing dose effect, those insulating layer will cause some trap charge, most likely positively trap charge. That is the one effect, right? Whenever an ionizing particle goes through this oxide material, they'll ionize the material. And one of the particle, like say either electron or holes, will remain. So typically electrons being mobile, they leave the system, holes get trapped. So that's the effect. So if holes are trapped in the MOSFET oxide, in terms of threshold voltage, how it will be reflected? Will threshold voltage increase, decrease, or remain same if there is a lot of positive trap charge in the oxides? Think about flash memory, yeah? Decrease, right? Because flash memory we trap electrons, threshold voltage increases. Here you are trapping holes, threshold voltage decreases. That means a program cell will become an erased cell after a lot of radiation. Similarly, if threshold voltage decreases, what are the other issues? You increases leakage, right? It cannot be turned off. If threshold voltage becomes below zero, that means at 0 volt transistor is on, huge amount of leakage will take place. So it will cause your DRAM retention issues, SRAM, noise margin issues and all. The second effect is called displacement damage. The displacement damage is more like damaging the crystal structure, right? So when heavy ion, for example, goes through your silicon atom, some of the silicon atom can be knocked off from the silicon material. So it changes the crystal structure, or it will cause recombination and will degrade the quality of the crystal. And then single event effect. So single event effect is more like a sudden transient current pulse, right? When a high energy particle goes through, say, your SRAM memory. So in SRAM, you store Q equal to 1, Q equal to 0. Because of sudden current pulse, this Q equal to 1 can be converted to Q equal to 0, right? So those kind of single event effects, which is more typical for, say, SRAM and DRAM, whereas total ionizing dose effect is more like a parametric degradation, long-term degradation, right? Over time, your threshold voltage will be degraded slowly, and over the time, your leakage will increase and your system will fail. Whereas single event effect is either it happened or it did not happen, right? When particle goes through in a very high speed, right? So it will be in picosecond time scale, right? In femtosecond to picosecond time scale, its beat will be upset or it did not upset. So those are the things we care about. So for non-volatile memory, typically this total ionizing dose effect is more important, because non-volatile memory, you have to retain data for long amount of time. The small degradation happening through threshold voltage change, leakage current will cause data corruption. Whereas for volatile memory like SRAM, DRAM, the single event effect becomes very, very critical. Okay, so let's look at each of these. This diagram is visible. Yeah, each of these effects a little bit closely. So this total ionizing dose effects, it is basically you're affecting this insulating material, right? Silicon dioxide, which is the most common in MOSFETs. So you will build a positive trap charge, right? Because of ionization of this oxide, right? So when oxide get ionized, electrons leave because of this electric field, right, towards the gate, whereas holes will be trapped inside or will remain inside the oxides. And that will cause threshold voltage shifts in MOSFETs, which in turn, will cause increased leakage currents and all. Questions in it? So anything you want me to a little bit elaborate, I'll be happy to elaborate, okay? So that's one effect. Displacement damage is like this. So you have a crystal, say each blue atom here is a silicon atom. When a heavy ion or heavy, say, particle, energetic particle comes in, knocks out this crystal atom. So crystal atom becomes a interstitial atoms, and that vacancy will cause a crystal vacancy, right? That is basically broken bonds that will act like a trap site. Electron can be trapped over there and all. So that's the effects. So in terms of electronic structure, right? This is this crystal atom. This is the energy bands. So any semiconducting crystal has conduction band, valence band. So basically, with each displacement damage, you are introducing energy states, possible energy states inside the band gap. So for semiconductor, band gap should be free. There should not be any electron or hole inside the band gap, right? That's why this band gap is called. Electrons should be in the conduction band, holes of the valence band. But because of this displacement damage, now these states are created inside the band gap. That means these states can act like a generation recombination center, right? So that means your recombination strength in the material increases because of this displacement damage. Okay, so now recombination inside the semiconductor is a bad thing, because that will increase your leakage current. That will increase, for example, for solar cell, it will decrease its efficiency when it is under sun. So these are the effects of displacement damage. And then finally, this single event effect, right? Single event effect is more like this. The single event effect predominantly affects a PN junction in the device, right? For example, total ionizing dose effects predominantly affect the insulating material. It can be silicon dioxide, right? There is a charge trap in the silicon dioxide after total ionizing dose effects. While a single event effect, if a particle goes through a junction like this, as you can see, along the path, it will create electron and hole pair. A significant electron hole pair will be created along its path. And this is a transient effect, right? This particle will go in a couple of femtoseconds because it's a very high energy particle. So it goes through the junction, but it keeps a trail of electron and hole. And those electrons and holes will be collected by the junction, because in a PN junction, you always find an electric field, inbuilt electric field, right? Just like in a solar cell, right? Solar cell is a PN junction. When light falls through this PN junction, it creates electron and hole pair. You collect electron from one contact, you collect holes from the other contact. Exactly happening in a much smaller time scale and much larger number. So that means in a small time, if you look at here, time here is in a picosecond time scale. You see a transient current pulse, right? Created because of this PN junction effect and carrier generation along this junction. So this current pulse can be enough to flip your SRAM cell, for example, or can be enough to flip your DRAM bit, right? So that's how you see single event effects or single event upsets in a memory because of this transient phenomena, which is carrier creation along a PN junction. Okay, any question on all these three effects? We talked about total ionizing dose effect, displacement effect, and single event effect. So these are the fundamentals. Of course, we'll connect all those fundamentals with the memory that we learned so far in this course. By memory, I mean SRAM, DRAM, and flash. Now, to give you some perspective on the units of radiation units, one is this rad is commonly used unit, which is called radiation absorbed dose, rad, or kilorad if you want to express in more. And there's another parallel unit, it's called gray, to represent the same, which is the 100 rad is 1 gray. So in many dosimeters and all, they will write gray or some units, right? So for example, for human being, right, 1020 gray is fatal. After 1020 gray of radiation absorbed dose, people can die, right? So that's the just to give you a perspective. When you do a CT scan, you absorb 1 rad, right? That means how much gray? 10 milligray, right? So you absorb that much of dose. So that's the just to give you an idea. So if it is hospital nurse and all which are working in say radiotherapy, for them 5 rad is the limit, right? For checkup and all. And then 10 millirad when you do a chest X-ray. So those are the some to just unit, or just to give you some idea that what this dose means, right? 1 rad means. In terms of electronics or in terms of silicon or MOSFETs, when you absorb energy from particle or high energy particle, some part is gone in ionizing the material, right? So ionizing means it will create electron hole pair, and some part will be gone to displace the atom, right? So for example, to create electron hole pair in silicon, you need 3.6 electron volt. Electron volt is the energy unit, right? Silicon dioxide more, and it can be converted into this number, which is the ionization constant in a material. That means per rad you can create 10 to the power 12 electron hole pair, right? When you absorb, so 1 rad, you multiply with this number, will give you total number of electron hole pairs generated. So some of these numbers you may need to use in the homework 6 that will be coming up after. So in this course, we'll have one more homework, the last homework, which will be on radiation effects on memory. So some of those numbers you may use to find out what is the threshold voltage shift. Right? Because to understand what is the threshold voltage shift, you need to understand how many electron hole pairs are trapped inside the material. So these are some of the things you can use for the homeworks. Okay, so these are the few steps how say total dose effects comes in a MOS structure. MOS means metal oxide semiconductor, right? Which is the gate stack, typical gate stack in a CMOS electronics. So this is your gate, metal gate. This is the oxide, silicon dioxide, and this is the silicon. So this is your MOSFET gate stack in horizontal fashion. Now, typically, you apply positive gate voltage, right? So that means your there's the electric field. So electron will move toward the positive gate terminal, whereas holes will move the opposite due to the electric field. So electric field direction is gate to silicon. So holes will move along the direction of electric field, whereas electron will move opposite to the electric field. So number one process in this radiation effects is electron hole pair generation. When a gamma ray passes through your insulating material, it ionizes the material. Ionizes means it creates electron hole pair. Right? So now electrons having higher mobility inside this insulating material will leave. They will leave most likely through the gate terminal. Right? Because gate terminal is positively biased. Whereas holes will move very slowly. Right? So they will move inside the oxide material at a very slow rate, and eventually they will be trapped if there is a defect location inside the oxide. So typically silicon dioxide has a lot of imperfection inside, closer to the interface, because when you go to silicon interface, those bonds, right? So those there can be some oxygen vacancy because of processing related issues. Those oxygen vacancies will trap those holes. So this is your hole trapping process, right? So number one, electron hole pair generation. Number two, hole transport inside the oxide. Number three is hole capture or hole trapping inside the oxide material. And number four, if the holes reaches this interface, then they will break silicon hydrogen bond, because at the interface of silicon dioxide, there is a passivation layer where silicon dangling bonds are passivated with hydrogen. When you make silicon and silicon dioxide interface, the dangling bonds of the silicon are passivated with hydrogen, typically. Now, when a hole will reach there, they will break those bonds. So your surface become depassivated again. So those are the issues, and because of the depassivation, there will be interface traps creation. So these are the four effects. So in summary, right, there are two main effects of radiation. One is your insulator will gather positive trap charge after radiation, or you will create some interface trap states, or your interface becomes trappy. That means electron mobility will be low, because all those electron hole transport happens through this interface, silicon dioxide interface. So if there is a lot of trap states, your mobility will degrade and all, right? So your threshold voltage will degrade. So those are the effects you see after radiation. Typically, thick oxides are more sensitive to TID, because in thin oxide, both electron and hole can escape. So if electron and hole both can escape, there is no net charge trap, right? So if it is a very thin oxide, which is true for, say, modern MOSFETs. So modern MOSFET like say 10 nanometer technology node, your oxide thickness will be very, very thin. So there, electron and hole both can escape, and you may see nothing has happened after radiation. Okay, but there are many cases where oxide thickness is large. For example, flash, right? In flash, you cannot have thin oxide, then there will not be data retention. In flash, you have to have fat oxides. That means flash will be much more sensitive to these TID effects. Questions? Okay, so I put a lot of references wherever I possible. So if any of those interest you, you can go and check it out. So in terms of math, so far we gave you a qualitative picture, right? Now we'll go a little bit quantitative. So for example, if you want to find out after radiation of say 1 kilo rad or whatever rad, right? So 100 rads, and TID will be 100 rad. How many holes are trapped in the oxide? Suppose you want to find this. Then these are the equation you need to use. These are very much like volumetric equations. So this is Tox times area, which is nothing but the volume of the oxide. What is the insulator volume? Thickness times area of the insulator, right? So this is your area of the, say, gate area of the MOSFET. This is the thickness, oxide thickness. So this is total volume times TID times your ionization constant. G0 is your ionization constant. I gave those numbers based on silicon dioxide. Ionization constant will vary. So this depends on how much energy you need to create electron hole pair, right? So when X-rays, gamma rays comes, how many electron hole pairs will be created? So that is the ionization constant. And then this EOX is the electric field dependent term, or not all X-rays, gamma rays will create or will lead to a hole trapping. Some electron and hole can escape after radiation. If both can escape, then there is no effect. In some cases, electron and hole can again recombine with each other. So then also there is no effect. So charge yield means what is the net charge yield after radiation. So what I mean is, for example, here, right? If you look at here, this electron and this hole, if they recombine again, then there is no effect of radiation, because there is no net charge being created, right? So this equation gives you net charge yield, which will affect your electrostatics, which will affect your threshold voltage, right? With threshold voltage, your data is encoded, for example, right? In flash, threshold voltage is the key. If you change the threshold voltage, your data is changed. So that's what this net charge will do. So this F is the probability. So what is the maximum value of F? If F is probability of charge yield, 1. Right? So many of this problem, we may give you the probability of charge yield is 1. That means you just consider F of EOX is 1. Then everything else you can just multiply to find out what is the net charge created because of radiation effects for a particular dose. So this is the probability factor that I talked about. So probability, that's why maximum is 1. So depending on what is the electric field in the material, right? This probability factor changes. If you put high gate voltage, there is a high field in the oxide. That means after ionization, there is a more chance that electron hole will be separated out. If there is no field in the oxide, then after an ionization, they can recombine again and your charge yield probability will be 0. So this chart is experimentally derived. This is the paper where you can find this chart. So this chart says what is the probability when you expose your material to cobalt-60 gamma rays through 10 keV X-ray source. So this is just to tell you this probability factor depends on the electric field in the oxide. Higher the field, higher is your probability to create net charge. Okay, and these are your ionization constant values, G0 values that I showed earlier. Right? This many pairs will be created per rad. Okay, so let's move on. So now here, this is one interesting things you can see. So this equation gives you how many electrons hole pairs are created and how many holes are eventually trapped, or what is the net charge yield, right? So for a circuit designer, that doesn't make any sense. Right? For circuit designer or from system point of view, all we care about is what is the threshold voltage shift, right? So every trap charge will cause some threshold voltage shift. So this equation gives you threshold voltage shift for given amount of trap charge. So if NH is your total number of trapped holes inside the oxide, if Cox is your oxide thickness, right? So then delta Vt will be change in threshold voltage. Now, if I have a MOSFET with this is your cross section, small cross section, say 20 nanometer by 20 nanometer node, right? This is your gate, source, drain. And you have another MOSFET which is bigger node. Source, drain, and gate. The gate area and gate oxide. Both has same oxide thickness. Which one will be more vulnerable to radiation? Or which one will cause? Suppose 1 kilorad radiation goes through it. 1 kilorad. 1 kilorad. One is wider area, large area, another is small area. Which will be more sensitive to radiation effects? Anyone? A MOSFET having large gate area, because W by L ratio you can play, right? And another MOSFET with small gate area. Everything else is same. Which is more sensitive to radiation effects? Sensitive means which will cause more Vt shift. Small one. Yeah, I mean, so that's where this equation comes in. So this equation tells you threshold voltage shift for a radiation dose, right? So NH, number of holes, yes, you are right. Number of holes could be more created in a larger device. The larger device also has a large capacitance, right? Smaller device has small capacitance, and you create less number of holes because area is small. So both is equally sensitive, right? As long as your oxide thickness are same. The answer is it does not depend on area. You look at number of holes created depends on volume of the oxide, right? So A times Tox. Whereas your oxide thickness, whereas your oxide capacitance of the MOSFET, right? With Q equal to CV, this C is also area dependent. So this area cancels out. What remains is Tox square of Tox. That means if your oxide thickness is large, your TID effects will be non-linearly increasing, quadratic dependence on the oxide thickness. So this is the x-axis, Tox, y-axis is your threshold voltage shift per 1 megarad. So as you can see, this is a log scale, right? So with oxide thickness, your threshold voltage increases significantly, threshold voltage shift. For example, if oxide thickness is 100 nanometer, right? Here, you get almost 100 volt shift because of 1 megarad radiation, right? Whereas if you go down, right, these days we are not in 100 nanometer oxide thickness. We are close to, for flash, for example, it is 20 nanometer in that range. Whereas for logic transistor like SRAM, DRAM, these access transistors are around 1 nanometer. So where you will see millivolt change. Axis is the millivolt, right? This is 1 volt, millivolt change with 1 megarad of radiation dose. 1 megarad is huge. Okay, so that means the state-of-the-art technologies or ultra-scale technologies, right, where oxide thickness is very, very small, TID is not a big issue because threshold voltage shift will be very, very little because oxide thickness is small. It doesn't really depend on area. With area, cancels out. If you have a wide area, you have wide capacitance. Yes, you can capture more radiation. You will be hit by more radiation particle, but accordingly, your capacitance is also large. Makes sense? So I hope that part is a little counterintuitive because you may sometimes think, okay, large area will be more sensitive because large area will be hit by more particles, right, over the time. But yeah, you will be hit by more particles, but your capacitance is also large. Okay, so this is one important thing, that okay, oxide thickness square. The other important thing is this equation will predict this line, this dashed line, that how much BT shift because of, for a given TID, right? TID here is 1 megarad. Now, in actually, you see this open symbol, this is a measurement symbol. They see, okay, if your oxide thickness is below, say 10, so 5 nanometer, 4 nanometer, right? This is 1, 2, 3, 4 nanometer. You see even much less shift in threshold voltage. Can anyone tell me why? I mean, this is the predicted that says if this is the number of holes, this is your threshold voltage shift. But in reality, you see even lower VT shift. So the reason is this equation does not include that hole will escape. This equation just tells you this is the number of electron hole pairs generated and this is the fraction, right? But as you make things very, very small, both electron and hole can escape as if nothing has happened. Right? That's why it doesn't follow this theoretical prediction after certain thickness. But overall, right, I hope you understood that as long as this insulating thickness is small, change in threshold voltage will be less, so it will be less sensitive. If the thickness is large, it will be more sensitive. It's pretty much independent of area. Now, if you look at the threshold voltage shift, right, so suppose you have a thick oxide, say 10 nanometer oxide, right, which is true for flash memory cell. Now, if you have a PMOS versus NMOS, that their threshold voltage shift will be very different. For example, you typically trap holes or positive charge in the gate dielectric after radiation. So when you have positive trap charge, the threshold voltage will shift towards negative direction, right? So VT will decrease. So this red card, right, or red line shows the oxide trapping related threshold voltage shift. So both NMOS and PMOS threshold voltage will shift negative. But in terms of magnitude, PMOS threshold voltage magnitude will increase because PMOS threshold voltage starts with a negative value, it becomes more negative. So VT of PMOS will increase magnitude wise, VT of NMOS will decrease, right? So that means NMOS will become more and more leakier, right? So this is a leakage current. So leakage current will increase with radiation effects. Now there is another effect which is the interface trap charge effect, right? So interface trap charge will cause further negative shift for the PMOS devices. Whereas for NMOS devices, interface trap charge will cause a positive shift in the VT, because interface trap charge for NMOS is negative interface trap charge. So that's why there is so for NMOS it is going down and going up because of interface traps. So this is a total shift because of radiation effects. One is this oxide trap charge, which is predominantly hole. That's why it is a positive trap charge, so negative VT shift. VIT, interface trap charge, depends on whether you are talking about in NMOS or PMOS. If it is PMOS, this will cause further negative shift. If it is NMOS, this will cause positive shift in VT. So that's the all the component that you need to know in terms of threshold voltage shift. Okay, and because of this threshold voltage shift, you will see leakage current in the IC will going up, because typically it is NMOS determined, even a CMOS circuit. And some of those shift, which is caused just after radiation, can be neutralized with time, which is called the annealing effect. Annealing effect can go on. So if you irradiate today, you see huge jump in leakage current, but after a week, if you measure the same device, you can see less degradation. This interface traps also takes some time to build up, right? So it is minimum immediately after radiation, but it takes time. So with time, you will see interface traps increasing, whereas oxide traps effects are going down. So in terms of IC, right, it primarily affects the timing characteristics, speed of the IC, latency, and the current driving capability of the device, right? We talked about in memory, for example, SRAM, DRAM, flash, right? We talked about the refresh interval, right? Hold time. All those timing parameters will be affected after radiation because of threshold voltage shift. Okay, so now let's look at some of those specifics. So far we talked about in general what happens after radiation in a MOSFET device. Now let's look at some of those example of memory. For example, let's start with flash memory. So this is your flash memory cell in a program state or erase state. It's more like a program state, right? So electrons are stored in the floating gate. Now a radiation coming through this particle will cause threshold voltage shift, right? So a threshold voltage shift will be given by how much holes are trapped in this blocking oxide, which is pretty thick, around 16, 18 nanometer thick. Whereas tunnel oxide is also quite thick, it's 8 nanometer or 8 to 10 nanometer thick. So these are pretty thick oxides. And because of those thick oxides, your radiation sensitivity is also large. Now you may think, okay, for space, maybe I designed my flash cell with thin oxide. What is the problem if you make thin oxide based flash? Charge will automatically leak. You don't need radiation. Automatically, because of thermal leakage, it will leak, right? Thermionic emission and other leakage. So you cannot retain data for long. So that's the problem. Okay, all the space agencies or space companies want to use flash because it is highly dense, low power, lightweight, very important. This is lightweight, highly dense, terabytes possible, but it is very sensitive. Fundamentally, it is very sensitive to radiation effects because high oxide thickness. So this is what will pretty much happen. Number one, you will create electron hole pair. Number two, electron will move out, but hole will never move out in this system, right? Think about, even if you make thin oxide, actually it will not help, because even if you make thin oxide, holes will go and meet with the electron in the floating gate. But there is no escape path for hole, right? I hope you understand. This is your energy band for blocking oxide. This is the energy band for tunnel oxide. Now electric field, right? Direction is both towards the floating gate. So after ionization, electron will leave in the control gate side, but hole will go to the floating gate. And floating gate is full of electrons. So they will kill or recombine with all those electrons. So your threshold voltage will shift. There is no escape path for hole, which was there for MOSFET, right? MOSFET thin oxide, hole can go out to the channel. But here, before going to channel, these holes will meet these electrons. So that's why it is very, very sensitive to radiation effects. And that is where I think I have a project, flash-based radiation sensor, where there is no escape path. If there is a radiation particle goes through this MOSFET, it will definitely cause conductivity shift. So that means flash memory can be used as a very good radiation sensor as well, because it's precisely this reason. There is no escape path for hole. You will see some effect, right? Same will happen in tunnel oxide. Tunnel oxide, the field is other way around, right? Typically, you give positive gate voltage, right? But here, floating gate is negative because you are storing electrons. Effectively, if this is your MOSFET, your gate is negative voltage, so electron will move now towards the silicon channel and hole will move towards the gate, and gate is full of electrons. So those electrons will be decaying, losing with time because of ionizing radiation effects. Questions? Yes?
So if it wasn't programmed, wouldn't it be able to escape the hole since the fields wouldn't be both going out?
Yeah, that's a good question. So he's asking if it is not programmed. This is a programmed cell, right? Programmed cell will lose VT. That is clear. Erased cell will gain VT. Because in erased cell, the electric field will be opposite. So electron will now fall in. So as if radiation is causing programming. So through radiation, you will program the cell. So this is here, you're through radiation, you're erasing the cell. So in fact, when the flash was first introduced early 1970s, it is UV erasable. UV light were used to erase the flash memory. It was not electrically erasable at the first generation of flash. If you look at my slides, I have some picture that they have to keep this dye exposed, because in order to erase the memory, you have to put it in under a UV light, and UV light will erase it because of this reason. So you can erase with light. You can, for erase set, if it is already erased, you can slightly see the programming, not too much. Because if it is neutral, right, if there is no field in the oxide, then there is no charge yield. So you need some field in the oxide, right, to create net charge yield. Okay, so let's look at this equation then. So how threshold voltage shift based on radiation amount. So change in floating gate charge, because floating gate charge will be directly proportional to how much holes are generated, or what is the ionization constant. Right, loss in floating gate charge, delta QFG is what is the, so we know the delta QFG will be total dose, ionization constant of the oxides, and the volume of the oxide. Right, here volume means both the oxides you have to consider, blocking oxide and tunnel oxide, because both will create holes. Whereas electrons being very mobile in the oxide, they will leave out generally, right? So after ionization, you can just think about holes are left, and hole has no escape path, they will recombine with the floating gate electrons. So that's why probability is 1. And this is your total capacitance. Total capacitance is only this blocking oxide capacitance, right? Because that is where charge is away from the control gate. So this is the equation we talked about when we solved flash memory related questions in homework 4, right? In homework 4, I'm sure you have used this equation. So this is the equation we're applying for understanding radiation effects as well. Now again, it's area get cancelled, and you get a threshold voltage loss equation in terms of blocking oxide times tunnel oxide, right? Or oxide thickness square. Yeah, the threshold voltage of programmed cells will gradually decrease with TID, whereas threshold voltage of an erased cell can increase with TID as well, to some extent. Okay, so device scaling. How device scaling will impact? So you have 90 nanometer node, 45 nanometer node, 20 nanometer node. How does it impact the radiation sensitivity of flash cell? Looking at the equation, as you go to the smaller technology node, will flash become more sensitive to radiation or less sensitive to radiation with smaller technology node? No, the sensitivity did not change, because this oxide thickness remains same. If you look at older node, higher node, smaller node, they pretty much has flat oxide thickness, because data retention criteria is same, right? 10 years, that remains same across the technology node. So whether you are a small technology node or big technology node, area gets cancelled, oxide thickness you did not scale. So that means flash remains vulnerable to radiation irrespective of technology node. right? Whether it's older node or smaller node, they remains pretty much equal. Little bit maybe improved because very slight decrease in oxide thickness happened in a very small technology node, right? Whereas in CMOS, there is a steep oxide scaling, right? Because of Dennard scaling, if you look at, we talked about it, every new generation, you scale the oxide as well. So there, radiation sensitivity has improved. Improved means it has become less sensitive to radiation. Like if you think about SRAM built with 90 nanometer node versus SRAM built with 20 nanometer node, 90 nanometer will be more sensitive to radiation than 20. Questions? Okay, I think to answer your question here, right? So you talked about program cell. So if you look at the threshold voltage distribution, this blue distribution is before radiation. You have a, so this looking at this distribution, what type of memory? It is SLC memory, it's single bit per cell. SLC flash, so because 1 bit per cell. So if it is erase cell, this will be a distribution, logic 1. If it is a program cell, this will be a distribution. So we understood this program cell distribution will shift with time because of loss of charge, whereas erase cell will shift up like this. Not equally high, because at some point you will reach the neutral level. So with neutral level, threshold voltage will not change. So in other words, this will be an energy band diagram for an erase cell. You look at this electric field direction is different now. For a program cells, electron moves out, moves away from the floating gate, because floating gate has so many electrons already. So they will repel those electrons. But if you look at an erase cell, right, erase cells sometimes have holes to start with, right? Because erase threshold voltage can be negative. So floating gate can have holes, right? So if those holes are there, then they will attract those electrons to come in after radiation. So this is the erase cell radiation effects. So electron will move towards the floating gate as if it is programming the cell. So as a result, you will see a little bit upshift in the erase threshold voltage. Make sense? Questions, anything so far? Okay, so this is about SLC memory, but these days SSD and SD card, these are mostly TLC memory. So TLC memory starts with very small margin, right? So anything that crosses below this reference will cause us a failure. For example, here. So if you shift from here to here, there is no failure detected. But the moment a tail crosses the reference level, then this area, right, will cause you error. For example, in one of the homework problem, you will be asked, or you are asked to find this area. So if you have a Gaussian distribution, you can find that what is the area of a Gaussian curve based on how much portion of the tail is crossing the VREF. So you can find how many cells got below VREF. That will give you your bit error rate in that memory, right? So if you have 16 kilobyte in a page, how many bytes or how many bits out of 16 kilobyte has crossed the threshold voltage? You can find it from the Gaussian probability. You can find it from this basic equation that we talked about. So I hope this will give you a very clear idea that how an SSD or how a real product is affected by radiation effects. So please look at for homework 6. Now, yeah, so just to give you an idea that TLC will be much more sensitive or much more error prone because TLC is used for increasing the density, but your cell structure remains exactly the same. Oxide thickness for each cell is remaining same. Only thing is you are binning the threshold voltage in a much tighter distribution. So this is our group's results. If you so in our group we do actually there are several students working on radiation effects on flash and other memories. We collected this data that before radiation, this is black is your measured threshold voltage distribution, and after radiation with more and more dose like 10, 30, 50 kilorad, you can see your threshold voltage median is shifting down, and not only median is shifting down, it is getting more and more wider. That means not all cells will be equally affected, right? If all cells equally affected, distribution width doesn't change. But here, there is a variability associated with who is hit by radiation, who is not. And based on that, there is another randomness. So distribution always represents randomness, right? So your just after program, your randomness is controlled by the programming algorithm. But under radiation, you become more and more wider. And wider is more problematic because why wider is more problematic than shift? Because look at here, the VT shift, right? So here we are not, say this is just for illustration, we have not considered widening. If it is not wider, right, the states are still distinguishable. All you need to do is reference shift. If you shift the reference in accordance with voltage shift, for example, these are your reference. If you shift it left, this voltage reference, you shift it left, you can still detect which state you are. But if it is wider, then two distribution will overlap. There is no margin in between. When two distribution overlap, then there is no way you can recover the data. So that is more, this VT widening is more detrimental from flash reliability point of view than just VT shift. Okay, so this is your sigma. VT widening becomes significant as we increase the total dose, right? Your VT shift, VT margin itself, right, in QLC is around 100 to 100 millivolt. So if you are eating away this margin with this VT widening. So this is the VT shift, median VT shift that decreases. Median VT decreases, but it becomes broader as well. So these are a few results from this work. Now it translates into a very high bit error rate. So 10 kilorad is very small amount of total dose, mostly LEO Earth mission for a couple of years. You expect, right, when you send your satellites, it should be qualified as 10 kilorad tolerant or something like that. Now, before radiation, the bit error rate was 0, whether it is MLC memory or TLC memory, right? TLC has some bit error rate before radiation, but less. After radiation, you can see your bit error rate is significantly high. So if your error correction capability is around 0.1%, right? So this 10 kilorad MLC will fail left and right, 10 kilorad TLC will fail left and right. So that's why there is a lot of data corruption happening in flash if on a commercial chips without doing anything. Questions? Yes, this is just to show different layer because we're talking about 3D NAND. 3D NAND has a number of layers. So this is 32 layer chip. This is 126 layer. So 128 layer chip. So yeah, you can find in which layer is more vulnerable than other things. But overall, just to give you a number, 10 kilorad is more than enough to corrupt data in flash memory if you don't do anything else. Now, what do you mean by if you don't do anything else? So there are some state-of-the-art radiation protection techniques in flash, which is something called error correction. So every page will have some error correction code. Even if there are some bit error, you can correct it. You can do read retry. Read retry is more like shifting your read reference voltage, right? So your default read fails, but I know that distribution has shifted down, so I'll also shift my read reference voltage accordingly. So this is called read retry, that I will try again. My default read fails, I'll shift the reference and I'll try reading again. So those are other techniques are used. So with these techniques, you can extend the radiation. So we have another paper on read retry. So if you use read retry, you can extend the radiation tolerance close to 50 kilorad for some memory, right? So these are some protection techniques typically used for state-of-the-art memory. So that's all about flash. Any question on radiation effects on flash? Yeah, today's class we are talking about total ionizing dose effects, right? Which is more like parametric, over time, slow killing. Next class we'll talk about single event effect, that a bullet goes in, right? That bullet, whether it will kill you or will not kill you, something like that. Here it is more like slow poisoning, that there is a slowly you are changing threshold voltage because of ionizing effect. Okay, so let's look at effects in DRAM. So what do you think in DRAM, how radiation will affect? More leakage, right? So your refresh interval should be increased accordingly because your access transistor, right? More than this capacitor, this access transistor will be affected by radiation because the access transistor is NMOS typically, and NMOS transistor threshold voltage will decrease, and over the time you will see that this capacitor will leak much faster. This is the gate leakage, right? Leakage of this transistor determines how much time you can hold the data in the capacitor. So yeah, that's definitely one. Decreased retention time. It can also be caused by current increase. So your total standby current, if you measure the DRAM standby current, that will also go up after radiation because this leakage and all. After, if it is heavily radiated, then you can see some functional failure. Functional failure means you cannot write, for example. You cannot read because of this change in threshold voltage and all. So those kind of functional failure can happen at a very high dose rate. So these are measured data from some of those SDRAM, DDR3 SDRAM, 4 gigabit, from a recent paper with cobalt-60 radiation source. And they can see error rate or error ratio with high and high radiation dose. We can see almost 200, 300 kilorad. That is the total dose needed to see high amount of failure in DRAM. Yeah, so I'll finish it off very quickly, but do you have any question on radiation effects on DRAM? Radiation effects in flash, radiation means total ionizing dose effect, right? Or TID effects is predominantly more for flash or non-volatile memory like flash because it is a slow effect, right? Parametric effect. Whereas for DRAM, you will see the single event effect, right? Which we'll talk next class. We'll solve few problems as well, which will directly affect the storage capacitor itself, storage node, right? So when radiation particle goes through it, this capacitor will discharge. That is a more hardline effects, right? In DRAM, but in DRAM, this is also an important effect. This leakage of this transistor, which will cause your refresh intervals, which you may compensate by increasing the refresh rate, but yeah, overall it will also cause failure. For SRAM, what do you expect? So this is your SRAM effect. So SRAM is a 4 transistor, 6 transistor, 4 transistor is their storage node, and there are 2 transistors. So what do you think? If gamma ray goes through it, will you see failure? So TID effects will not cause directly data corruption in SRAM because these 2 transistors, right, is a positive feedback. If you lose charge from here, this PMOS will replenish that charge. For example, this is Q equal to 1, right? That means this capacitor is charged. So this PMOS, if you lose some charge because of leakage, this PMOS will immediately replenish it. Because SRAM is called static RAM, right? So anytime you lose this storage charge, there is a PMOS transistor to replenish it. But you will see this kind of effect, right? So your threshold voltage of these individual transistors are changing, NMOS changing, right? NMOS threshold voltage will be down. And we talked about when you talked about SRAM, your read margin depends on the threshold voltage. So that means read disturb will increase, for example, right? So you will, you have to operate the transistor at high voltage. You cannot operate at a low voltage, right? Your retention voltage means when SRAM is not doing anything, you are holding the data, right? That time to reduce leakage power, we reduce the voltage, supply voltage, right? So to retain data, you don't need 3 volt. To retain data, maybe 0.5 volt is good enough. But after radiation, that minimum retention voltage will increase. You cannot keep it at 0.5 volt after radiation because those transistors are now more leaky, right? So their stored data becomes less stable over time due to leakage. So this leakage effect will have impact on data retention voltage, read-write disturb during read and write, this floating node that can go up, right? And that will cause disturb because your threshold voltages are now less. Your butterfly diagram will be distorted, right? If you remember, SRAM has a butterfly diagram, 2 inverter, back-to-back inverter. There are 2 eyes. Those eyes should be big. Small eyes is bad because small eyes means less noise margin. But after radiation, those big eyes will become small. What I mean is, if you forget about, SRAM has this kind of noise margin. So this noise margin will decrease with radiation effects. And your standby current will increase, leakage current increases with radiation, and if it is too much radiation, you can see functional failure. Now, functional failure, right, comes from where? Or what can cause functional failure in SRAM? Functional failure means you cannot read, you cannot write. Those are mostly coming from peripheral circuits, because when you talk about a memory array, it is not just the memory cells. There is a row decoder, there is a sense amplifier. If sense amplifier also will be degraded, right? Your sensing margin will go down, right? Because of radiation, because radiation will cause threshold voltage shift. So if your sense amplifier cannot amplify some voltage, right? You cannot sense it. So after high amount of radiation dose, those peripheral circuits will be also affected, and overall you cannot read, you cannot write. This is the functional failure, which will see a global failure, right? Entire row is failing. Whereas bit flip is more like a stochastic event. In one page, you may see 1 or 2 bit got upset. Right? These are not massive or global failure. So that's how you can distinguish between a peripheral failure, which will be a massive global failure that you cannot read, you cannot write, or entire word got flipped, entire row got flipped, and this and the cell failure. Cell failure will be very much stochastic, random, uniformly distributed in a randomly located locations. Okay, so I will stop here today, and maybe we'll continue our discussion on radiation effects in the next class, specifically from single event point of view. Thank you.